Okay, so for this first problem here, we have that the variable pH in the formula pH is equal to negative log of H plus represents the level of acidity or alkalinity of a solution, and H plus in moles per liter is a concentration of hydronium ions in the solution. So this is a pretty applied question, but I think it's important to just kind of recognize this is the equation that we're going to be using. Up here, the pH is equal to negative log of H plus. With this is one of our important variables and the units. So first we want to determine the pH of the following. We have a tomato with H plus is equal to 6.31 times 10 to the negative 5 moles per liter. So if you plug that in for A, we have the pH equal to negative log of 6.31 times 10 to the negative 5. And that, if we look at it, we only have one unknown as a pH. So we can go ahead and plug that into the calculator. And that will give us that the tomato has a pH of 4.2. Moving on, we're going to find milk of magnesia. We're given that this is the H plus value, 3.16 times 10 to the negative 11. So again, just using that formula that we were given, we have pH is equal to the negative log, just kind of again, copying from this, of 3.16 times 10 to the negative 11. Now plugging that into our calculator gives us a pH of 10.5. So those are our two answers for part A. And then moving on to part B, we are given the opposite information. So we're given the pH and we need to determine the H plus. So I guess to solve this, we're going to need to do a little bit of rearranging of the original formula that we got. So I'm going to do that over here. I have pH equals to the negative log of the H plus concentration, and we want to solve for that. So to undo the log, we're going to raise 10 to the power of everything. So I have 10 to the pH is equal to 10 to the negative log of that H plus. So now we're going to have 10 to the pH is equal to 10 to the log of 1 over H plus, or just 10 to the pH is equal to 1 over H plus. And that here, from here to here, just comes from the fact that there's kind of a negative, there's an understood 1 in front of that. And so if we bring the power in, we have log of H plus, log of H plus to the negative 1, which is equal to that, 1 over H plus. Now moving on, we can rearrange this by just kind of taking the reciprocal on both sides. So that way we have H plus is equal to 1 over 10 to the pH. Perfect. So now looking at the first one, we have an onion with a pH of 5.6. We know that H plus is equal to 1 over 10 to the 5.6. And plugging that into our calculator is going to give us a concentration of H plus is equal to 2.51 times 10 to the negative 6 mole per liter. And now make sure we have our units correct. pH doesn't have a unit, so we're good on that. But concentration should have a unit, so that's why the mole per liter is coming in. Going on to the next one, we have baking soda with a pH of 8.4. So this is just going to be given through the same formula. H plus is equal to 1 over 10 to the 8.4. And plugging that in is going to give us a value of 3.98 times 10 to the negative 9. Okay, that's 3.98 times 10 to the -9, and we want to make sure our units are right, so we're going to include those as well. There we go, perfect. Moving on to the next one, we're given that log base b of 2 is about 0.356, and log base 3 of b is about 0.565. So using that, we want to approximate the value of log base b of 24, show all work. So for this one, what I would say is we could go ahead and just kind of say, okay, we'll solve for b using this, but since we're given 2 and 3 here, what I'm going to do is I'm going to take this 24 and I'm going to break it down into factors. So if we think about it, log base b of 24 is equal to the same thing as log base b of 3 times 8. And now using our product to sum identity, we can say, okay, well this is the same as log base b of 3 plus log base b of 8. We were given this, right? We know that that is 0.565. Now, what we want to do here at 8 is notice that this is going to be the same thing as 0.565 plus log base b of 2 times 2 times 2, or 2 cubed, right? Now from here, we can take the power out. So it was 0.565 plus 3 log base b of 2. Again, we know what this value is. So this is going to be 0.565 plus 3 times value of log base b of 2 was this. So plus 3 times 0.356. And then plugging that into our calculator will give us that log base b of 24 is about equal to 1.633. Then I'm just going to go ahead and put that over here. So log base b of 24 is about equal to 1.633. Moving on to problem 36, we're asked to use the change of base formula, get to that in a second, to evaluate log base 6 of 23 using either base 10 or base e. We want to show all work for that. So the change of base formula looks like if I have log base a of b, and I wanted to get it to log base c, this is the same as doing log base c of b over log base c of a. So that's how we would kind of convert to a different basis for this. So if I wanted, for example, this question is using log base 6 of 23. So I'm going to use log base 6 of 23. If we want to get that into log base 10, so c is 10 here, I would say, okay, well then I'm going to evaluate log base 10 of 23 over log base 10 of 6. And then plugging that into the calculator is going to give us a value of about 1.750. Now, just to be thorough, it said base 10 or base e. So I'm going to do this for both and say, okay, well, what if I wanted it in base e, right? So log base 6 of 23. Here our new base is e. Now remember, log base e, that's just the natural log. So this is going to have a value of the natural log of 23 over the natural log of 6, which, again, putting that into the calculator, is going to give us a value of 1.750 approximately. So log base 6 of 23 is approximately equal to 1.750. Perfect. Okay, so now moving on to number 37, we are asked to solve the following exponential equations, giving an exact solution and an approximation. And then we need to show our work. Okay, so for this first one, for A, what I'm going to do, I'm going to take 5 to the 3x minus 2 equal to 625. Take the natural log of both sides, giving natural log of 5 minus 2 is equal to natural log 625. Now my power here can come up front. 3x minus 2 times natural log of 5 equals natural log of 625. And then because the natural log of 5 is just a number, go ahead and divide everything by natural log of 5 to get 3x minus 2 is equal to natural log 625 over natural log of 5. And then from there, we just need to figure out what x is. So add 2, and then divide everything by 3. So that way, we have x is equal to the natural log of 625 over the natural log of 5 plus 2, whole thing divided by 3. And then plugging that into your calculator is going to give us that x has a value of 2. And that just comes from this right here is 4. So we have 4 plus 2 over 3, 6 over 3, which is just 2. Moving on to the next one, I have 6 to the 2x minus 5 minus 8 is equal to 12. So I'm going to take this to say x. 6 to the 2x minus 5 minus 8 is equal to 12. So first step here, I'm just going to go ahead and add 8 over to get 6 to the 2x minus 5 is equal to 20. Now taking the natural log of both sides gives me a natural log of 6 to the 2x minus 5 is equal to natural log 20. Here the power can come up front. So I have 2x minus 5, natural log 6 equals natural log 20. Then I'm going to go ahead and distribute that natural log of 6 out, just because it's being multiplied, so I'm going to go ahead and distribute that. So I have 2x natural log 6 minus 5 natural log 6, sorry, this should be 20, is equal to natural log 20. Now continuing up here, I'm going to add 5 natural log of 6 to both sides, so that I have 2x natural log 6 being equal to natural log 20 plus 5 natural log 6. And then the last thing is that x is being multiplied by 2 and also natural log of 6, both of which are just numbers. So I'm going to divide everything by 2 natural log 6. So on the left-hand side, I'm just going to have x. On the right, I'm going to have all of this over 2 natural log of 6. So natural log 20 plus 5 natural log 6 over 2 natural log 6. And this, when we plug that into the calculator, has a value of about 3.3360. So I'm going to go ahead and copy that back over here. We have x being equal to natural log 20 plus 5 natural log 6 over 2 natural log 6, or about 3.3360, just because we need it to 4 decimal places when we approximate it. On to the next one, I have 4 to the x plus 2 is equal to 6 to the 3x minus 4. So I guess first step, take natural log of both sides. Natural log of 4 to the x plus 2 is equal to natural log of 6 to the 3x minus 4. Here the powers can come out front in both. So I have x plus 2 natural log 4 being equal to 3x minus 4. natural log 6. And then from here, what I'm going to do, so I'm going to go ahead and distribute these. So I have x natural log 4 plus 2 natural log 4 is equal to 3x natural log 6 minus 4 natural log of 6. And now my inclination here is that we want to get all the x's on one side and everything else on the other. So what I'm going to do, so I'm going to subtract x natural log of 4. I'm going to add 4 natural log of 6 all in one step. So on the left-hand side, I'm going to have 2 natural log 4 plus 4 natural log 6 being equal to 3x natural log 6 minus x natural log 4. Now notice that all of the x's are over here, and all of the y's are on the opposite side. So since these both have an x in common, what I'm going to do is I'm going to go ahead and factor that out. So that is going to be 2 natural log 4 plus 4 natural log 6 is equal to x times 3 natural log 6 minus natural log 4. Now the last thing to do is kind of notice that we have x times this whole function. If we want to get x on its own, we need to divide that all over. So I'm just going to divide everything by 3 natural log 6 minus natural log 4 to give us that x is equal to 2 natural log 4 plus 4 natural log 6 over 3 natural log 6 minus natural log 4. And then plugging that into the calculator gives an approximate value of 2.4918. Again, just because we need to go to 4 decimal places. And then finally, we're looking at e to the 2x plus 2e to the x minus 24 is equal to 0. So what I want to point out first is that this kind of takes the form of a quadratic formula, right? Because we have e to the x squared plus some constant times e to the x minus a constant being equal to 0. So I'm going to try and see if we can do a substitution that makes this into a quadratic formula. So I'm going to say let u be equal to e to the x. And then using that, and say, okay, well, this e to the 2x is going to be e squared plus 2e to the x is just plus 2u minus 24 is 0. And that one's nice and easily factorable into u minus 4, u plus 6 being equal to 0, which gives us the solutions of -6 and +4. Now, it's important to go back and kind of plug in and determine whether or not this is actually, either of those are actually viable solutions. So what we're going to say is, okay, let -6 be e to the x and 4 be e to the x. The way that we're going to solve both of these is going to be exactly the same. Take the natural log of both sides. So you have natural log of -6 is equal to x. Natural log of 4 is equal to x. This one is not a possible answer, though, because we have a negative log, so that one can't be it. So we know that our solution is going to be x equals natural log of 4, and plugging that into the calculator is going to give us approximately 1.3863. Perfect. Now moving on to problem 38, we were asked to solve the following logarithmic equations. We were supposed to give an exact solution and approximate to 3 decimal places as needed. Showing all work. Okay, so this first one, I'm going to say we have log base 3 of 2x plus 5. That's equal to log base 3 of 5x minus 13. So what we can do here is go ahead and raise everything, raise 3 to the power of both sides. So I have 3 to to the log base 3 of that, of log base, so 3 to the log base 3 of 2x plus 5 is equal to 3 to the log base 3 of 5x minus 13. That's going to cancel the log, so we just have 2x plus 5 equals 5x minus 13. And then from here, we just want to solve. Go ahead and add 13 to both sides. Subtract 2x. So we have 5 plus 13 is 18, being equal to 3x. Divided by 3 gives that x is equal to 6. And that is a valid solution because there's nowhere in our logs that we can plug in x equals 6 and get a log of a negative number. So that's something that we want to pay attention to here, is that if we plug in our value of x, do we end up with a negative? So now moving on to letter B, we're going to say, okay, log base 6 of 7x minus 2 equals 1 plus log base 6 of x plus 5. What I'm going to do here is I'm going to go ahead, I'm going to subtract this log base 6 of x plus 5 over. So I have log 6, 7x minus 2 minus log 6 of x plus 5 being equal to 1. These two logs can be combined by the subtraction to quotient rule. So that'll be log base 6 of 7x minus 2 over x plus 5 is equal to 1. Raising 6 to the power of both sides gives us, this log will go away. So 7x minus 2 over x plus 5 equals 6. Now, we can multiply everything by x over 5, or x plus 5, to get rid of what's in the denominator here. And we'll go ahead and distribute that. So I have 7x minus 2 equals 6x plus 30. And then from there, just adding 2 to both sides, subtracting 6x, is going to give us x is equal to 32. So no approximation required here. Then moving on to the last one, I have log base 2 of x equal to 4 minus log base 2 of x minus 6. Yep. So I'm going to do something similar. I'm going to add log base 2 of x minus 6 to get log 2 of x plus log 2 of x minus 6 is equal to 4. Now these two can be combined into one log. I'm going to go ahead and do that and also distribute to get log 2 of x squared minus 6x is equal to 4. Now raising 2 to power both sides, get rid of this log. So x squared minus 6x is equal to 2 to the 4th, plugging that into the calculator, gives 16. Now if we look at it, this is pretty similar to a quadratic equation. So what we can do now is say, okay, well if I subtract 16, I get x squared minus 6x minus 16 is equal to 0. Then going ahead and factoring that, it's going to give us x minus 8, x plus 2 is 0, or a solution set of x equals negative 2 or 8. Now, like we said earlier, we do need to check to make sure that these are available, like that these are possible solutions to our question. So plugging in 8 up here and up here, that would give us log base 2 of 8. That's okay. Log base 2 of 8 minus 6 is 2, so that's also okay. But our issue comes in when we plug in negative 2. So if I have log base 2 of negative 2, that does not exist because we have a negative inside of our log. So negative 2 is not a solution, which leaves us with just x equals 8. we go. Now moving on to problem 39, we have to do a little bit of algebra. We want to solve for the indicated variable, right? So something that we can kind of notice in A is that, or for part A, is that we want to figure out what t is. So I'm going to write that over here. We have A is equal to P times 1 plus R over N to the N t. Before we do any taking natural logs, I'm just going to go ahead and divide this P from both sides. I'm going to get rid of this on the right and just leave us with A over P is equal to 1 plus R over N to the N t. And then from there, what we can do is go ahead and take natural log of both sides. That's going to give us natural log of A over P is equal to, this power can come out, so it's going to be NT, natural log 1 plus R over N. Now from there, solving for t is pretty easy because we have it's either multiplying by n or this natural log. So what we want to do now is just divide that whole thing by n, natural log 1 plus R over N. That's going to cancel this out and this out. It's going to leave us with t being equal to natural log of A divided by P over N natural log 1 plus R over N. That will be our solution. Go ahead and write that over here. That was equal to natural log of A divided by P over N natural log 1 plus R over N. And then for part B, coming back, we want to solve this for B. So I'm going to go ahead and write that equation over here. We have log B minus 1.7 is equal to 2.3 m. So what I'm going to do first is I'm going to get this log B on its own. So I'm going to add 1.7 to both sides to get log B is equal to 2.3 m plus 1.7. Now, it's important to recognize that these aren't going to combine like terms because this doesn't have an m on it. It's just 1.7. So we're going to end up with this. And then finally, to cancel out that log, we want to raise 10 to the power of both sides. So 10 to the log b, that's just going to be b. That's equal to 10 to the power of 2.3m plus 1.7. That I'm just going to copy over here. So b is equal to 10 to the 2.3m plus 1.7. There we go. And then lastly for this page, we have number 40. So Matilda and Horace open a retirement account with $120,000. How many years will it take for the money to grow to $800,000? If it grows at a rate of 4.5%, compounded monthly. We are rounding to the nearest year. We want to show all work. So what we want to use for this question is our periodically compounded exponential function. So that is going to be A equal to P times 1 plus R over N to the N t. If we notice, this equation is exactly the same as what we saw for in 39a up above. So we know that we're looking for t, so we can go ahead and use this equation that we already determined. So I'm going to skip a step here because we already determined that. I'm going to say, well, t was equal to natural log a divided by p over n, natural log 1 plus r over n. And now what are each of our pieces, what do each of those mean? So our beginning value, p, is equal to 120,000. And our amount at time t, a, is equal to 800,000. Now from there, we know that the rate is 4.5%, which is the same as 0.045. And then lastly for n, that's just the number of times it's compounded per year. So if it's compounded monthly, that means that we are going to do it once a month, which means that we compound 12 times a year. So t is going to be equal to natural log of 800,000 divided by 120,000 over 12 natural log 1 plus 0.045 divided by 12. Now plugging this into our calculator, it's going to give us about 42.237 years. And keeping in mind that we want to round to the nearest year, we would say that it would take approximately 42 years. Perfect.
All right, so for number 41, it says the population of a rural community was 3,050 in 2010, and then the population increased to 3,500 in 2015. And then it says, assuming exponential growth, okay, so for part A, we have to find the growth rate to 4 decimals and as a percentage. And so if we just start at part A, we know that there are a couple of ways to express an exponential function, right? And so for this problem, let's just do the form P of t well, actually, hold on, I'm going to write this so you guys can see it. Make sure you guys can see it. It's going to be P of t is equal to P naught e to the k t, where P of t is our population, right? So I'll just like circle population and kind of point here. That's going to be our population. And so let's say that our starting year is 2010. And so that means that P naught is going to be equal to our amount at 2010, which is 3,050, right? And so then to find our growth rate, we know that our growth rate is just going to be this K, right? And so to find our growth rate, we can just plug in this other point that we're given. We're given 3,500 in 2015, right? So we can set up an equation and say, let's see, 3,500 is equal to our original amount of 3050 times e to the k. And now for our t, we said our starting year was 2010, right? And so 2015 is 5 years after 2010. And so our time in this case is going to be 5. And so then to find our k, that's just going to be, well, first we can divide by 3050 on both sides, right? By 3050. And so then we're going to get e to the k times 5 is equal to 3,500 over 3050. And then for our e, we can get rid of that by doing natural log of both sides, right? So then we'll get, that's going to cancel out the natural log and the e. And so then we'll get k times 5. Oh, sorry. It's going to be k times 5 is equal to the natural log of 3,500 over 3050. And then to get rid of the 5, we can just divide by 5 on both sides. So then we get k by itself. And so then we get k is equal to, well, it's going to be natural log of 3,500 divided by 3050. And that's all divided by 5, which gives about 0.0275 or about 2.75%. So that's going to be, and I'm just going to kind of catch all of those. It's going to be our K, right? And so then for part B, it says estimate the population in 2022 if the trend continues. So now that we have our K, we have our exponential function, right? So if I write it all out, that's going to be P of t is equal to our initial value of 3050 times e to the 0.0275 t. And so if we're going to estimate the population in 2022, and with respect to 2010, well, 2022 is 12 years after 2010, right? So the t that we're trying to look for is 12. So then we're going to say P of 12 equals 3050 times e to the 0.0275 times 12. And so then, if we just plug that into our calculator, we get 4242 people. All right. Okay, so for number 42, it says a sample found at a dig site was determined to have 68.78% of the C14 still remaining. Use the model Q of t is equal to Q naught e to the negative 0.000121 t to determine the age of the sample. And then we'll round to the nearest year. Okay, so in this case, I think it's helpful if we define our variables. So Q of t, let's just say Q of t equals remaining, or I won't say remaining, I'll say quantity of C14 sample after t years. So then, let's think about this. So it wants us to find the nearest, or the age of the sample. So that's years, right? So we're looking for t. And so our QT in this case, well, it says the sample found was determined to have 68.78% of the C14 still remaining. So we know that our QT in this case is going to be, or Q of t, sorry, is going to be 0.6878 times our initial quantity, our Q naught, right? And that's going to be equal to that whole equation that we have, the Q naught times e to the negative 0.000121 t. And so then we're just solving for t at this point, right? So we can divide by Q naught on both sides. So then we get 0.6878 is equal to e to the negative 0.000121 t. And so then to get rid of that e, we take the natural log of both sides, right? So natural log. So that's going to kind of cancel the natural log and e out. And so then we're left with negative 0.000121 t, it's a negative, is equal to the natural log of 0.6878. And so then to get t by itself, we just divide by that decimal, right, that negative decimal. And so then we'll get, or come over here now, t is equal to natural log of 0.6878 divided by negative 0.000121. And so then if we plug that into our calculator, we get, I think, like 3093. And so then we'll just say the sample is about 3,093 years old. And that'll be our answer for number 42.